Our group members are Adam, Yorenzi, Zoe, and Bethany, and our technical description was focused on geometric dimensioning and tolerancing.
In the world of engineering and manufacturing, certain parameters, along with other lines, symbols, and notes, are used to indicate sizes of geometric features on part drawings. These are called geometric dimensions. Geometric dimensions give the ideal or nominal value for what the part size should be in a perfect world. They refer to the geometry of the feature and not the material properties. However, there is an abundance of variation due to manufacturing processes inhibiting the part size from being the exact intended value. Because of this variation, tolerances must be used. Tolerances define the limits in which the geometric dimension is able to vary while still producing a good part. Tolerances are the difference between the maximum and minimum limits. Here is a very simple GD&T example of an internal feature on a part. It shows that the diameter of the cylinder should be 0.875 units with an upper tolerance of 0.005 units and a lower tolerance of 0 units.
GD&T helps bring clarity to all the problems that come with describing how much variation is allowed between features. This figure shows the square zone, where the parts fit perfectly, and also the circle zone, which are the areas encompassing the corners of the square zone that could still fit.
Geometric dimensioning and tolerancing is essential for effective communication by providing a consistent measurement system available across different processes and disciplines. This system allows for any engineer to look at a certain part geometry and immediately visualize the desired outcome, all while being easy enough to teach to first-year engineering students. GD&T assists in specifying the orientation, location, and form of the component and its features. This is incredibly important when it comes to understanding detailed engineering drawings and has been successfully used by engineers, manufacturers, and designers in a variety of industries including automotive, aerospace, manufacturing, commercial, electronics, and design. GD&T is also important for accurately calculating tolerance analysis. The part geometry and their tolerance zones allows for calculation and analysis of extreme boundaries. As a result, the effect of manufacturing variation is able to be analyzed before the part is produced and allows for issues to be addressed in a timely fashion.
GD&T serves many important roles in a manufacturing environment. One of those roles is to save the manufacturer money. GD&T ensures that no more material than what is necessary is used in the manufacturing of any given product. GD&T can also save the manufacturer money by not allowing a production process to become more difficult than it needs to be in order to ensure an acceptable product. The images on this slide demonstrate just that. The picture on the left shows the different surface finishes made by a machining operation. The worst or roughest surface finish is on the left, while the best or smoothest surface finish is on the right. The graph on the right side of the screen demonstrates that the smoother the surface finish, the more expensive it is to produce. Let's now look at a real example on the next slide. This is an example of a cylindricity tolerance. Cylindricity is defined as a condition of a surface of revolution in which all points of the surface are equidistant from a common axis. A cylindricity tolerance is defined as a tolerance zone bounded by two concentric cylinders within which the surface must lie. So in order to ensure that a tighter cylindricity specification is met, the manufacturer will need to spend more money during the manufacturing process to ensure a more precise or smoother surface finish, so that all the points on the cylinder are inside the tolerance zone. If the cylindricity tolerance zone is larger, the company will be able to be more lenient during the manufacturing process, as the surface finish will not need to be as smooth. For example, in the figure 3 above, all points on the surface lie within the tolerance zone, although neither look particularly smooth, so these parts are acceptable. However, if the tolerance zone was made smaller, the company would need to spend more money to make the surface more precise. Many of the different types of tolerances use a datum as a reference. A datum, as defined by the website GD&T Basics, is a theoretical exact plane, axis, or point location that GD&T or dimensional tolerances are referenced to. Datums will be seen in some of the next slides. Now let's look into some specific types of geometric tolerances. This is a cylindricity tolerance. A cylindricity tolerance ensures that a supposedly cylindrical product is truly cylindrical, at least within a tolerance zone. The tolerance zone for cylindricity is defined as two concentric cylinders, between which all points of the feature being tolerant must lie between. This figure demonstrates a cylindricity tolerance in which the total deviation allowed is 0.030 inches. A cylindricity tolerance is useful in the case of a cylindrical shaped part that needs to fit into a hole. This is a position tolerance. A true position tolerance is used when one wants to precisely define the location of a feature on a part. In this figure, the engineer uses a position tolerance to define the location of a hole using the datums A and B. the engineer defines the hole as 30 inches up from datum A and 20 inches to the left of datum B. A true position tolerance is useful when the location of a feature on a part needs to be exact in order for that part to function properly. This is a flatness tolerance. A flatness tolerance is used when one wants to ensure that the surface of a part is flat. A tolerance zone for the flatness tolerance is two parallel planes in which each point of the surface being tolerant must lie between. This figure demonstrates a flatness tolerance in which any point on the surface is allowed to deviate a total of 0.05 inches without exiting the tolerance zone. This is a perpendicularity tolerance. A perpendicularity tolerance is used to ensure that two features of a part are perpendicular to one another. In this figure, it is shown that the orange surface needs to be perpendicular to datum A. Rather than using angles to ensure perpendicularity, a tolerance zone of two parallel planes is used. Similar to a flatness tolerance, the planes are a set distance apart. If all the points on the feature being toleranced are within those two planes, the feature is deemed perpendicular to the referenced datum. This is a runout tolerance. A runout tolerance is used to ensure that each outer point on a circular cross-section of a cylindrical part stays within a tolerance zone defined by a circle. The difference between runout and cylindricity is that runout only deals with a circular cross-section, while cylindricity deals with the entire cylinder. Runout tolerances are always referenced to a datum axis. This figure demonstrates an example of a circular runout tolerance in which the cross-section at point A must not deviate more than 0.030 inches if the part was rotated and continuously measured at that cross-section. Finally, let's look at a parallelism tolerance. A parallelism tolerance is used to ensure that two features on a part are parallel to one another within a tolerance zone. The tolerance zone for a parallelism tolerance is given by two parallel planes with reference to a datum. This figure demonstrates a parallelism tolerance in which all the points on the orange surface must lie within the two planes parallel to datum A that are 0.030 inches apart. If all the points lie within these two planes, the surface is deemed parallel.
Different types of tolerances can be used to specify tolerance limits. These different types include bilateral, unilateral, and limit dimensions. Bilateral tolerancing, shown in image A, is where the upper and lower deviations from the nominal value are equal to each other. So this part is allowed to be 2.5 units long, plus or minus 0.005 units. Image B shows a unilateral tolerance, where variation is only allowed in one direction, either up or down, but not both. In this image, the part is allowed to be 2.5 units long, plus 0.01 units, but it cannot deviate in the negative direction. Image C shows limit dimensions, which are completely different from the first two types of tolerances. Instead of having a nominal value along with an upper and lower deviation, limit dimensions simply give the minimum and maximum allowed values for that specific part size. This part's length is allowed to range from 2.495 units to 2.505 units.
Looking ahead, geometric dimensioning and tolerancing will prove to continuously gain importance. As technologies further develop, geometric tolerances will need to become stricter in order to ensure quality. As the manufacturing of products grow increasingly difficult, engineers will face more and more challenges in setting the geometric tolerances for these products.